Pseudo NMOS logic gates. In Chapter 1, a number of NMOS logic gates were introduced. In this session, pseudo NMOS logic gates will be revisited in a somewhat more formal manner, where extensive use will be made of the equivalent resistor approximation. This session will also deal with the how to choose the device sizes for NMOS logic gates. An example of NMOS logic is the straightforward realization of the exclusive OR function. The exclusive OR function or the exclusive OR is defined by y is equals to x1 plus x and S2 is equals to S1 S2 bar plus S1 bar S2 is equals to S1 S2 plus S1 bar S2 bar whole bar is equals to S1 S2 plus S1 plus S2 bar whole bar. A logic circuit that realizes this function is shown in figure. A pseudo NMOS realization of this logic circuit is shown in figure B. The NOR gate A is realized by transistors Q1, Q2 and Q3. The second order NMOS gate composed of transistors Q4 to Q7 is a compound gate. It realizes both the NOR gate C and the AND gate B by a series connection of drive transistors. Notice how the series connected transistors Q5 and Q6 are chosen to be wider than the parallel transistor Q4. The general form of typical NMOS logic gate is shown in figure. It consists of single p-channel load transistor between VDD and Vout and has its gate connected to a bias voltage. Figure A, a logic circuit realization of the exclusive OR function. B, an NMOS realization of the exclusive OR function. Here you can see the figure, a generalized pseudo NMOS logic gate. In addition, there is a network of n-channel enhancement drive transistors between Vout and ground. Each of the drive transistors in this network has its gate connected to an input depending on the logic values of the inputs. The network of drive transistors will either provide an infinite impedance between Vout and ground, and in which case the output will be VDD, or will provide a low enough impedance so that Vout will be pulled low to a zero. In the event the network of drive transistors is low impedance, such impedance must not be larger than that of a single enhancement transistor with its gate connected to VDD and having its W by L at least one half the size of the load transistor. This constrains the minimum W by Ls of the drive transistor. The maximum W by Ls of the drive transistors are constrained by the desire for speed, making them larger than necessary, makes the logic slower than it need to be for two reasons. First, it increases the parasitic capacitances of the internal nodes of the gate. Second, it increases the output load capacitance of preceding gates. Taking W by Ls too large does not cause the gate to function incorrectly. Before describing how the WLs of the n-channel network should be chosen, it is necessary to state some important theorems regarding approximate transistor equivalent that will be used often in this test. Thank you.